Good afternoon.
Hello.
Okay, let's see, there's 13 people here, 49 people in the class. Most of you know me, have had me before. So I think you know the style I generally use, at least in a face-to-face setting. Some of you had me for CS 225 last semester, which was also online. And if you took CS 225 with me, you were introduced to some of the agile concepts, and that's what we use in this course. But this semester, we use it in a team setting instead of an individual setting. So let's get started here. First of all, I didn't have a live lecture for the introduction. Were there any questions about the introductory material, the expectations for the course, or how we're going to do this? Everything's clear? Or at least you'll figure it out as we go along. You trust that I'll explain things. That's a bad expectation, right? All right. Okay, Brandon. All right, let me get this up then. And so I suspect, again, I ran this course face-to-face several years ago, and we met two times, 2 hours a week. I'm sorry, 2 times, 2 hours each time. And I would do the first hour of lecture, and then the second hour would be workshop. And of course, the teams would also meet outside of class. So what I thought would make better sense here is have 2 hours of lecture on Monday and office hours on Wednesday, which is effectively workshop. The main thing is to give you enough lecture materials so that you have all the information you need, and then give you time to get your work done with your teams. So I'm trying to be a good manager. A good manager is supposed to give you all the tools you need to do the job and get out of your way. So I'm trying to give you what you need to know and then get out of your way. This lecture is just a basic introduction of software engineering as a discipline. Nothing specific to the course, other than a lot of warnings about how hard software engineering is. And then we follow up next week with Agile. Let me bring up the schedule because I've already forgotten. No, come on now, you can do it. Let's see here. Okay, so we start out with, if you look over here on project activities, the first 4 weeks are just getting teams formed and ideas for projects formed. And then we go into sprints, so there's actual project work, and there's 5 of those. So what we'll start with the next couple of weeks is discussing the Agile process and give it a fair amount more depth than we did in CS 225, give you an understanding of what deliverables happen in each sprint. We talked some about requirements in 225. Here we talk more about it. Requirements and requirement specification are difficult. Design, configuration tools, and so on. So the idea here is to try to give you what you need to do to get the job done in your project a week or so ahead of the need for it. And I had a meeting with our tutors slash TAs, Priscilla Carbo and Luke Crump. And they approved this sequencing. They thought this was a good sequencing of the material. The way this will work, we'll break down into teams. There's 49 people in the class. Teams work best with 4. So that means we'll have 12 teams. One team will have 5. And then of the 12 teams, we'll assign 6 to Luke, 6 to Priscilla, and then they become your mentors and tutors. And I hope they get to sit in on some of your meetings and watch your interactions and also guide you. So we're not trying to throw you out in the woods here. The idea is to give you a lot of freedom to let your team do what they need to do in a way that works for the team, and still you have access to myself and to the TAs for some expertise. Okay, now if I say something that puzzles you, by all means, just stop, let me know, ask a question, jump right in, unmute yourself and ask the question. Okay, this has got a lot of material in it, this particular module, because it's trying to cover a wide swath of software engineering in general. So I'm going to go through it nice and slow. I would much rather have a discussion than a lecture. So again, if you have any thoughts or questions, by all means, jump right in. So what is software engineering? Notice what keeps showing up in these top 3 definitions. Sound engineering principles: economic, reliable, works on real machines. The second one, principles of computation and mathematics to achieve cost-effective solutions. And then the third one, systematic, disciplined, quantifiable approach to delivery maintenance of software. Some of this is hidden by those 3 definitions there in the top with the blue words basically are telling you the same things. The middle one is a little bit more computer science oriented, I think, about talking about computation and mathematics, but they do bring in cost effective. And we're going to go this over and over and over again. Sound engineering principles. Well, what is engineering? What, someone says, oh, I'm going to school, I'm going to be an engineer. And then your aunt always says, oh, what are you learning? And it's a good idea to have one-liners for these kinds of things. If you can take what you know and condense it down to one top-line sentence, I've always found that to be a good exercise. And so, what is engineering in itself? Well, it's a discipline, right? It's a set of accepted procedures and protocols to try to develop products. And historically, these products have been physical. Tractors, buildings, airplanes. Now in software engineering, it's non-physical, but it's still a product. And you want to try to develop good sound processes, right? So that's what it really comes down to, processes, right? Engineering is a mindset and a set of established processes to produce these products. And you want to produce them in a cost-effective way so that people buy your product, and on time so that people buy your product, and high quality so that people buy your product. And if you back off from the specifics of the language of those 3 things, high quality and on time and of good cost are embedded in those 3 statements. And we'll see this like 5 or 6 times throughout this lecture. Okay, so the reason why it takes 4 years to become an engineer and more years after that to become a good engineer is because you have to learn a lot of stuff, and a lot of it is about process. It's not all about, for you double E's, it's not all about circuit equations. It's about process. For you AEs, it's not all about the drag and lift coefficient in equations, it's about process. So in this class, we focus a lot on process. How does this differ from computer science? I like the one-liner. Computer science is at its core, the core question in computer science. What can a computer do? We have this thing called a computer. It's a mindless automaton that performs some kind of operations. What can it do? That's really what computer science is asking. And that gets broken down into different things, architecture, languages, algorithms, things like that. What can a computer do and what are its limits? And people have been asking this since before we had computers in the way we understand them in the modern sense. And then software engineers say, okay, now we think we know what a computer can do. Now that we know what a computer can do, what can we make with it? What products can we build with it? What can we do with it? So the software engineering is asking more about, okay, we know what a computer can do. Now I want to make a product that is focused on the computer. So notice we're getting into a lot of other ranges, right? Computer science is very much mathy sciencey in its purest form. And software engineering needs some of that, right? You need to understand what a computer can do. You need to be able to understand how how to literally program. But you also need a bunch of other stuff, and it's process stuff, a lot of it is. How do you build teams? How do you make a team work well together? What makes a team work well? What makes a team work poorly? Those kinds of questions. How do you manage projects? I've got 500 people working for me. How the heck am I going to manage that? So software engineering gets into this management engineering type stuff, right? Process. So it's a blend of those two things. And because it's a blend, of course, we, in theory, would not expect someone with a software engineering degree to know as much about pure computer science. But on the other hand, the computer scientists might know a lot about computer science, but might not know anything about how to make a product. It's become really common in universities these days. If you get a computer science degree, you have to take at least one software engineering course so that you have a better understanding of not just how to write a program in a lab for a homework assignment, but how to actually develop software in a structured, meaningful way, the way it's done in the real world. So we focus on process. All right, we're going to focus on process. Maybe we should know what a process is. It's a shame I'm showing these slides, because I could have, if this was face-to-face, I'd say, what is a process, right? Instead, we can critique this thing. A process, what is a process? Oh, it's a series of steps involving activities, constraints, and resources that produce some kind of intended output. What do you think about that? Can you critique that? Can you improve it? Is there parts of it that you are like, I'm not sure what they're saying here? A couple meta lessons for the course, right? One is, you already knew intuitively what a process was. Maybe you didn't have a clear definition for what a process was, but you had an understanding, an intuitive understanding. My belief is it's always good to explicitly know what you know. Don't just have an intuitive understanding or something. Try to actually write down the definitions for it. It forces you to think through what you think you know. And number two, when someone gives you a definition like this, the first thing you should try to do is tear it apart. Being very skeptical is a very good engineering trait. When someone gives you a requirement, try to tear it apart. When someone gives you a process, try to tear it apart. When someone gives you an idea, try to tear it apart. Now, you do that in a constructive way. The goal is to improve it, right? Okay, series of activities, constraints, and resources. What are they talking about here? Activities, constraints, and resources. Activities, that's the things that people do. What would the constraints be and what would the resources be? You know, let's go with software engineering. Here you are, you're in a class, you're going to form a team, and you're going to produce a product by the end of the semester.
Your constraints could be your requirements, and then resources would be like your teammates and what software you should use in your machines.
Right. So resources are people, right? Rather dehumanizing, but people. And the software you're going to use. Do you have access to machines? Do you have to use the school machines? If you have to use the school machines, are the labs closed on the weekends, or can you use them 24 hours a day? These are resources, right? And then you have constraints on those resources and constraints on the task. Some constraints are you're taking 1 of 4 or 5 classes this semester. You are time constrained. It would be unfair of me to ask you to spend 40 hours a week on this class because you have a constraint there. You have money constraint. Maybe you want to buy some cool software development tool. By the way, they're free. Right? You can get them for free, but you might have money constraints. Senior design, so often they want to build, they have to build a hardware software system, and the hardware costs money. So there's a constraint. The faculty says you are only allowed to spend X amount of dollars on your project. That's a constraint. Time constraints, money constraints, physical resources, room space. The fact that we're online is a constraint of sorts because the agile process works best in a face-to-face setting. So there's a constraint. Now, a lot of you are on campus and maybe you'll be able to meet on campus, but you might have a team member who's online. And then you have the constraints of the actual job that the product is supposed to do, right? The actual requirements. The customer says, I want this to do this, and it has to do it so fast. If you're working in a safety critical environment, it has to have a high reliability rate, low failure rate. You can't have single point failures. You can't have things where if it fails, people die. Those kinds of constraints. And then the activities are the processes and the methods by which you get things done, right? So, what is your organizational scheme and your plan, step 1, step 2, step 3. The steps are fuzzy, right? Real world steps are integer based. If you walk up a set of stairs, you're either on the 3rd step or the 4th step, right? But these steps sometimes can be fuzzy and that, they kind of blend into each other. They're not always linear. You go forward, you go take, 1, 2 steps forward, 1 step back kind of thing. A lot of software models exist. We'll briefly talk about some of them later in the semester. We'll talk quite a bit about the Agile Scrum model. There's again, quite a few Agile variants, but we're going to use Agile Scrum. It's really popular out in industry now. Everybody's doing Agile. And it'll be popular for, the next probably 10 or 20 years, and then something else will come along. Okay, some people think this is a subdiscipline of systems engineering. So, gosh, systems engineer, what is that? When I worked in industry in the 80s, I would encounter systems engineer. It was a brand new discipline. Software engineering and systems engineering are new disciplines. They're only like 30, really been recognized as disciplines for about 30, 40 years. As opposed to, math, which is 7,000 years old. So I would meet the systems engineers in my company, and I'd say, "Oh, systems engineer, what do you do?" And they'd kind of joke, "Yeah, I'm a systems engineer, and I don't know what that means." And then it evolved, right? Systems engineering evolved, and by the 90s, we could say, "I'm a systems engineer, and other people don't know what I do." And now finally, we can say, "I'm a systems engineer, and I really know what I do, and I can explain it to other people." And what is it that you do as a systems engineer? You incorporate systems. And if you think about complex entities in your life, those are systems. And they can be, I think I used an automobile example in the recorded lecture. An automobile example, you think of an automobile as a thing, but it is a system of things, right? It's got a fuel delivery system. It's got an engine. It's got a drivetrain. All of these are different systems. And often designed, right, by not just different people, but maybe by different companies, different corporations. Shock absorbers, brakes, the suspension system was probably outsourced. The brakes were probably outsourced. And then the company putting the car together becomes more of an integrator than a builder. Same obviously is true of aircraft and other large entities like that. But think in terms of even organizational systems like the university. The university is a system. There's different components to it. There's people that have to deal with the facilities. There's people that have to do with scheduling. There's people that have to deal with human resources. There's people that have to deal with student affairs. These are all different components that come together and form a system. So it's not so much a mechanical system, but an organizational and behavioral system. Now, why would people think software engineering is a subdiscipline of systems engineering? That's nuts, right? Well, think of large software products. Number one, large software products tend to be built by different groups of people as standalone or semi-independently development. And then they take these software systems and incorporate them together. If you've ever looked at worked with the FAA or looked at how the FAA software systems work, they're all built by different people at different times. and then they try to incorporate it into one large airspace, one large air navigation system. And by the way, part of what's happening with the modernization of the FAA, or the modernization of our airspace around the world, is to take advantage of the fact that we have all this great computational power that we didn't have even 15 years ago, and try to make these systems all play with each other. So what happened is people would develop, the FAA would say, gosh, it would be cool if we had a tool that did this, and someone would build that tool and it would do a very specific job. And then the FAA would say, it would be really cool if we had a tool that did this, and they'd build another tool. Someone else would build another tool that did another specific job. And now they're finding that the information that those two tools have really should go and talk to each other, but they can't, because they were built by different people at different times. There was no commonality. There was no sense of eventually we're going to incorporate this into a single system. Boeing, a number of years ago, landed a very lucrative contract to create ERAM, which is a way to try to be a one-stop shop and handle all of these things. And so ERAM does a whole bunch of different stuff. It's primarily a software system. But if you start to think about other software systems, gosh, ATM bank machine, navigation guidance system for the space station, flight support for Boeing 777, all these things, look at what you have. You've actually got software and hardware working together. The navigation guidance system is not just a software product. Why? Because it has to use physical sensors, physical receivers, antenna, in order to receive signals, to do the work, to figure out where you are and where you're going. Almost every system ultimately becomes a software-hardware blend. Well, hardware is clearly outside of software engineering, therefore we're talking about systems engineering. And again, we come back to quality software, on time, within budget, and good, cheap, and fast, pick two. Okay, questions, jump in anytime. Layered technology, this is just another way to look at. People spend a lot of time trying to look at these things and look at processes to try to decide how can you develop processes that make sense. As a student, you may not have encountered that too much. You're kind of down in the weeds, right? We're teaching you, okay, here's how you do an if then else statement, right? Here's really tiny, narrow keyhole thing. But ultimately, in order for this stuff to be useful and for you to be employable, you need to be thinking in terms of larger things about, oh, wait, processes. People who are thinking about processes and processes by which you develop processes, right? These are like meta level people that are thinking in the big pictures. So there's a lot of talk, a lot of work that's done with processes. This is done in education too. We talk about what's the best way to teach a lesson, what's the best way to put a class together. Once I put a class together, what's the way to put a curriculum together, a degree program together? Right? So we can keep getting larger and larger and larger in scope. The basis of this is a quality focus, and then we say process, and then methods and tools. And I would ask you, okay, quality focus. So first of all, how does that even relate to process, right? That sounds like a big jump. There's no relation there. What's the relationship there? What do you think? Go ahead.
Quality focus. I lost my train of thought.
Yeah, it's okay. Sorry, I interrupted you. Let me ask you this question. How many of you guys, when you did your software in a previous class, did tests on your software? Yeah. Now, why did you do that? What's the point of that? That's a waste of time, right?
Gotta make sure it works.
Make sure it works, right? Did you have a process by which you tested? In other words, was that a standard thing you did when you wrote your software? You would always run some kind of a test on it.
Yeah.
And then how formalized were you with that? Would you say that you would create actual test cases and then run your software against those actual test cases? I know if you took CS225 with me, you did.
Yeah, you gotta get those edge cases.
At least I tried to make you do that, right?
Sometimes
Yep.
it's just run it
So-
through and try to break it as much as
Sometimes,
possible.
right. Sometimes it's very ad hoc, right? So if your process, if you're going to have a quality focus, how does that relate to process? You embed quality in your process. How do you embed quality in your process? You embed things like code reviews where you have people look at each other's code. Engineers check each other all the time. That's what you do. When I was in industry, I would say 30%, maybe more of my time was spent just checking other people's work, not doing original work. You check each other. You build in code reviews, you build in customer reviews, you build in tests, you build in requirements reviews. So there's a lot of review. In other words, someone does work and then other people look at it and say, yeah, that makes sense. Or, oh, wait a minute, there's a problem here. So the quality gets built into the process. And again, when you get down to safety critical items, then the process might have some more safeguards in it. You know, you might do testing. You know, if you're building physical items, you often test them in such a way that you try to destroy them. You try to find out what their limits are, or you test them in these off-nominal conditions to see if maybe that propane tank, we think it won't blow up. And how can we figure out if it won't blow up? Nowadays, the big thing is cybersecurity. So how might you build cybersecurity into your process? That would be a quality focus, right? Well, you would probably hire some white hat hackers and see if they can get into your software. That's part, you build it in the process. Now, what are the methods? The specific methods are, you know, this is kind of fuzzy, right? The specific methods are the smaller steps that you take to implement the process, and then tools. So what's the difference, say, between a method and a tool? What might a tool be in software engineering?
I guess like your IDE.
Yeah, IDE, that's a great tool. Version control software, that's a great tool. They're building more and more tools, AI that can scan your program, run your program, try to find faults with it. Formal models where you mathematically model your software and try to make determinations about it. Even formal proofs and things like that, these are tools.
Like servers, sometimes if you have a lot of tests you need to run, you can always have those tests running in the background.
Right, right. Yeah. In fact, have any of you guys done JUnit testing? We should require that this semester. That would be good. JUnit testing is a great tool because it's basically you set up your tests in software as tests, and then when you compile your code, you can say, okay, run a test on it. And every time you change your code, you can automatically run all the tests, so that if you add something new that broke something old, you find out about it immediately. It's a great tool, and it's
Is that similar to Bamboo in the Atlassian stuff?
I'm not sure. I'm not too familiar with the Atlassian tools.
Okay, never mind.
Yeah, but if Bamboo is an automated test suite, then it's the same thing. Yeah. Here's some websites. All right, so go see these. By the way, oh, you know what? I keep finding and losing this thing I should do for ethics, and I'll try to put it in the ethics document. For a while, the Department of the Navy would publish every year a listing of all the ethics violations they found in the Navy. It's a big document every year. It's a great read. It's full of officers requiring their subordinates to run personal errands for them, or people skinning off the top and that kind of stuff. JUnit and NUnit testing. I have not used NUnit. It might be just the difference between the name of the tools. Maybe. I know JUnit is a specific tools testing suite. Where did you use NUnit? What was the context? What language? C Sharp. There you go. So it's probably basically JUnit for C Sharp. And as you know, C Sharp and Java are very close cousins. Okay. So here's the problems. We don't have to worry too much about cost, but in this class, right? Other than there's only so many of you, right, on a team, so there's an implied resource shortage there, right? How do you manage cost in other projects? Is you just throw more people at the problem in people charge hours to the company, so that's throwing money at the problem. So quality is hard to manage, cost is hard to manage, schedule is hard to manage. The software industry has a very bad reputation because people will overpromise their software up front. We can do it in 9 months. It ends up taking 18 months, and we can do it for $100,000. Well, you got to pay those employees for 18 months instead of 9, so now it's $200,000. Or instead of $1 million, it's $2 million. And then the quality, as you know, can be difficult. We've all used crappy software. We've all been frustrated with software, especially, it's interesting to me, and I haven't done this very much, but you go on the App Store now, and basically almost anybody can create software, throw it up on the app stores. What does that mean in terms of quality? It means you're going to get a really wide range of quality. You're going to get some really awful programmers out there. And then you download their stuff and it's buggy and it's defective, and hopefully you don't get a virus, and you kick it out and you pick another one. And hope that the user reviews are accurate. But it's a nice experiment in quality, right? Because basically it's open, not open source, but it's a free market where it's really easy for any idiot who thinks they can code can throw something on the store. Additional problems, of course, it's getting larger. I always say back in the 90s, we had, 1 meg of RAM, 50 megs of hard drive, something like that. And it took about a minute and a half for my computer to turn on. And now I've got, I don't know what I've got in this machine. It's not much compared to what you guys have, but people are running around with, terabytes of hard drive and multiple gigs of RAM. And it takes about a minute and a half for the computer to start up. And why is that? If the chip is so much faster, we used to have 50 megahertz chips, and now we've got gigahertz chips. If the chips are so much faster, why does it still take a minute and a half to power up the computer? Well, because if you give people an empty bucket, they're going to fill it. The same thing happened with bandwidth on the internet. Remember the old dial-up modem days? Basically, what were the web pages? They were all text and little tiny pictures. And now it's all video, whether you want it or not. You go to a web page and go to a news site, and they're going to show you a video, and you try to stop the video, and they put it down in the corner. It's like, no, I don't want the video. What are they doing? They have access to the bandwidth. They're going to use it. They're going to fill it up. So software becomes larger and more complex. As the machines get more capable, the software gets larger. The larger something gets, the more complex it is, the harder it is for a human to understand it. And again, to the point where, software was hard to understand before. How many of you guys, I don't know, this might be an embarrassing question, okay? If you're embarrassed, I guess don't answer. How many of you guys created software projects so far in your careers that were large enough that you were a little bit confused about what was going on in some of the places? You were a little bit confused about why it worked and why it didn't work. Yeah. I mean, that's fairly normal. Fairly normal. It's certainly normal when you're having a failure, when you're debugging, right? But even when it worked, there's parts of it like that. And think about it, your code was maybe only several hundred lines of code, or maybe, maybe a little bit bigger than that. But now you think about 10,000 lines of code, 1 million lines of code. And that 1 million lines of code is interfacing with other software that is also 1 million lines of code. There's no way that people can understand the details of it. Harder for the understanding, harder to do project management. The more people there are on a project, the harder it is to manage them. That's why I like to cap the teams at 4. It's large enough where you get team dynamics, and it's small enough where it's still manageable. Once you get teams of 8, 9, 10, then in a classroom setting, it can be difficult to manage that. It's even difficult to get shared vision, that everybody understands what's going on. Agile teams seem to work best in that 4 to, gosh, maybe a dozen is starting to stretch it kind of range. Okay, this is all bad news. This whole lecture is bad news, right? It's like, this is how hard software is. And by the way, this is a software course, right? So You know, if you're a software engineer, I don't want you to change majors, okay? There is hope. Fred Brooks, this is, I forget the date of this book, we could, you know, look it up. Identified some inherent software difficulties, which he called essences. And I like this chart. I really like this: complexity, conformity, changeability, and invisibility. And the first, you know, complexity we already talked about. Not only are software systems large, but they're going to interact with other software systems that are large. Invisibility, we've talked about before in CS225. You know, most engineers have the benefit that they build a physical product. And if you build a physical product, you know, you can build mock-ups of it, and you can hold it in your hand, and you can hit it with a hammer, and you can turn it around, and you can do fit checks and things like that. For example, in order to build wire harness, I worked on a satellite program for a while, and in order to build the wire harnesses for this satellite component that we were going to build, they built like a plywood mock-up of it. It was dimensionally correct. And then they built the wire harnesses in the plywood mock-up. And then when they transferred it to the real deal, it would work. Try that with software, right? Where's your plywood mock-up of your program? It's invisible. You can't touch it, can't see it. Very hard to understand it. You know, that just makes the ability to understand the software that much more difficult. Conformity and changeability are a little tougher. On changeability, you may have already dealt with. You know, the old line is software is never done, right? Oh, I just want to do one more thing. I just want to do one more thing. I just want to do one more thing. Well, why is that? Because if you build a car and then you want to change it, you know, you're talking about cutting metal. That's kind of a drastic act. You know, people know when they're changing the car. But when you're changing software, they're like, oh, it's just the software guys. They can change that, no problem. It's constantly changing. And then once you deliver a car, let's say, I keep going back to the car example for some reason. Once you buy a car, right, that car roughly stays the same for the lifetime of the car. But once you buy software, what happens? Oh, time to upgrade, right? Every 6 months, every once a year, something like that. You get these notices, please upgrade your software. It's changing constantly. And not only does the software change, the environment changes. So now you've got software on your machine, and now you get a Windows upgrade or a Mac operating system upgrade. And yet software has to work in that new environment. So things are changing all the time. And then conformity, conform to the environment they're deployed in. So again, you know, why does Java run on a Java virtual machine? What was the point of that?
Was it something about it has a specific way it needs to build the code and turn it into binary or something like that?
Yes, it has a lot to do with that. Yes, that's correct. That's a good answer. It can compile and run anywhere. Exactly. They're solving the conformity problem. If you were to compile all the way down to executable code, like those of you that took the C class did, and then you take it to a different machine, that executable may not run due to operating system differences, due to chip set differences. You know, it's possible that your code would not be portable. It would not conform to the new environment. But so what the Java people did right off the bat, they said, we want high portability of our code. We will require that the code runs on a Java virtual machine. And so what's happening is Java virtual machine makes sure that your code will conform to whatever machine you want to run on. But look at the work that you had to do, that they had to do. So these are inherent different. I like this chart. I think this is a good thing for people to know. I think it's good to keep in mind when you are designing software, when you are designing something. Remember, these are the challenges you're going to face. And again, it's good to explicitly know what you know. These would be good things possibly in a job interview. Oh, you know, what challenges do you see? Blah, blah, blah. Well, complexity, conformity, changeability, and visibility. Non-essential software, they're still difficult. Machine complexity, low-level machine components can act weird. Limited access to the machine. Now, this says here, this is how old this is. Long turnaround, batch processing. How many of you guys have done batch processing? I don't see that anymore. Computers used to be a lot slower. So what you would do is you submit a job and it was called a batch job. So when I was doing modeling you know, I would have a finite element structural model of my satellite components, and I would build those models. And then, you know, I would leave work at say 5 o'clock in the afternoon. And the last thing I would do is I would submit my job to the central computer that was in the building, and it would run that job overnight. And then the first thing I did in the morning is go down in the basement and pick up my output, my paper output. You know, so I had real limited access to the machine, because basically I could get one run a day. And if it was wrong or I was confused about something, I had to wait a full 24 hours.
That's coming back with AI, because it just takes forever.
Yeah. So AI, the training times can be very long, and there's a lot of work done in that. Now, what's happening now is, because you have access now to Google Cloud services and things like that, you may have access to a machine, but that doesn't mean you have, oh, my dogs are going nuts. There's certain something's going on outside. You may not have access to the machine. So I had a nephew whose job was to go around the country for a restaurant chain, and every time they opened up a new restaurant, he would install all the software they needed to run that specific restaurant. Whoever was developing that software may or may not have had regular access to the most current you know, cash registers they were using in inventory, in computers that they were going to run their inventory systems on and things like that. So you usually have good access to a machine nowadays, right? Our laptops can do all kinds of stuff. You know, the labs in the computer can do all kinds of stuff. You want to do really high-end, lots of processing, you can go to cloud services, often for free or for very low cost. But that doesn't mean you have access to the machines that your software will be deployed on. In fact, we had this problem in senior design a couple of years ago. That was a team between, it was a team capstone between the machine, mechanical design and software design. So the mechanical design people were building an automatic lawnmower, right? A people-less lawnmower. And our people were designing the software for it. And one of the problems was they rarely had access to the lawnmower. So how can you test? And then programming environment. Oh, okay, different environments. Now I'll be interested to see if this works even within your team. If you have a team of 4, you probably have a homogeneous programming environment. You're probably all going to use Eclipse, but maybe you've got one person who just loves IntelliJ and they want to program on their part of the code on IntelliJ. Maybe you've got a Mac user, you know, 2 Mac users and 2 Windows users. It'll be interesting to see if that kind of thing pops up. Once you get into very many people, it's pretty easy to run into these different kinds of troubles. And again, in the real world, you may have dozens, hundreds of people working on a software project, or you may have multiple teams from multiple companies working on pieces of the project that need to come together. Any more questions? Okay, let's get down into more bad news, more issues, product issues, people issues, process issues. Product issues. Analysis and design. This is tough in and of itself. We don't push algorithmics in this university too much. And quite frankly, I have a little bit of a confusion about how much it should be pushed, given that we live in an object-oriented world these days. You remember, in an object-oriented world, what you want to build are objects that have methods, and each method should be really small and do one specific little tiny job. That's considered good design. Whereas in the old days, when you had a procedural program that went from top to bottom, and you thought about how to solve a problem, you would create an algorithm to solve that problem. And the algorithms were more central to the idea of programming. With the object-oriented world, the object interaction is more central to the idea of programming, and it may be you're less likely to see people talk about algorithmic solutions. No, that I'm saying less likely. I'm not saying it's gone. Here's where algorithmic solutions show up a lot. Cybersecurity, that's still a big deal. And AI, still a big deal. not the AI learning processes, right? The algorithms that people develop for the machine learning. So there is a home for these things, but that kind of stuff is tough. Analysis of your code, that's tough. It's not impossible, right? It's just, these are hard things to think through. If it was easy, software engineers wouldn't be paid so much. Right? If it was easy, everybody would do it. Software construction. Now, you guys have all gone through software construction. You've all been frustrated because your code didn't work. Hopefully. If you haven't tested yourself, you haven't stretched yourself enough, right? You've all gone through software construction in different classes, different assignments. How much do you like that act? The act of sitting there and programming. How many of you guys really love that? And how many of you guys really hate that? How many of you guys love it, but you get frustrated with it? That's me. That's me. When I'm programming, it's like, I don't like people in the room, even, my family, even my dogs leave the room because I'm just constantly cussing up a blue streak. It's just constant. That's my process, right? So software construction, we've all experienced some frustration with that. That's the easy part of the job. Yeah, exactly. Yeah, when the code works, right? That's the easy part of the job. If you do all the hard stuff up front well, then the software construction, the actual programming, is a relatively trivial task because all you're doing effectively is documenting what you've already designed ahead of time. It's the figuring out of the design ahead of time that is the harder part, but the payoff is huge because there's no way you can actually create good or working software of any complexity whatsoever unless you've done the work up front to get a good, strong vision of what you're doing and get a good, strong design. Now, this is going to seem very contradictory to what the Agile process says, but there's actually a blend here. It actually works out. In the Agile process, what you get is a good, strong notion, schematic of what's going to be designed, and you flesh it out piece by piece. As you flesh out, because it's an Agile process, you have the ability to keep updating your schematic, but you don't just jump in head first without having an idea of what the whole looks like. Okay, then software testing. People study everything. People study testing. What makes a good testing technique? How do you know that you've covered the software with good tests? How do you know where you've left holes? These are good questions to ask. And there's a couple different techniques that people tend to use. How do you know your tests are good? How do you know your tests match the requirements? These are things that are issues that have to be worked through. The ones you don't get to see in school so much are deployment and maintenance. And the reason you don't see maintenance, of course, is, when maintenance, we're talking about software that hangs around for 3 years or 3 decades and has to be continually upgraded. Several years ago, I was at a conference and I met a woman who worked for State Farm Insurance, and she was in charge of a group of people. She was a manager who was in charge of a group of people, and they had a huge software product that they used internally. And it was written in C code. And at the time, it was like 25 years old. So it's probably 35 years old now. And her whole team of people, their job was just to keep it alive, keep it running. Software maintenance is a big deal. And very likely, a lot of you are going to get jobs, not where you're developing brand new software. Most people, when you go to get a real paying job, most people get a job working on software that has already been developed and built, and you're either maintaining it or extending it, or maintaining it by adapting it to a new environment or extending it to do a new thing. Very rarely will it be that you get to start out with a clean slate and build from scratch. Once you gain experience, if those opportunities come along, the experienced person will be the kind of people they'll look for to do that. That's one good thing about doing your own software products, right? You get to start with a clean slate and build your own thing. And we also don't worry too much about deployment. Although I have deployment issues already, because I will get in CS225, I'll have people that say, well, it worked on my machine, and I'll watch them. They'll show me and it works on their machine. They send their code to me and it won't work on my machine. That's a deployment issue. So I just fail them. That's fair, right? And that's a good idea. Okay, let's talk about people issues a little bit. These are things that you may not think about until you go through it. By the way, for your project, I'm going to encourage you to try to find a real live customer. And by a real live customer, I don't mean a paying customer, but I mean a customer who will take your product when you're done with it and use it, and who is not part of your team. So last semester in CS225, I teamed up with Sean Dougherty of Human Resources, Professor Dougherty, and he gave me an idea for several projects, and a couple of the students took him up on it, and they met with him a couple times, and he basically became their customer. And of the 2 people that tried it, one of them delivered, I think, a working product that he can actually use now for his classes to let students experiment with test design and things like that. So as we get talking about the project more, I'll bring this up, but I hope you do find a customer on campus who needs something done. Maybe it's a club, a student club. Maybe it's a professor. Maybe it's somebody else. Now, it's not going to be something that we're going to fold into the actual Embry-Riddle software with using IT necessarily. That's more than this course needs, but a standalone product that actually somebody uses. And that way, you know, once you're done, it's not like this project just was forgotten and never existed. You know that somebody's going to be able to use it somewhere. So be thinking through that. All right, what issues do we have? Customer, I think instead of going through these slides, I'm just going to stick on that. What issues do we have between the customer and the developer? Well, the customer comes to you and says, I need software that does X, Y, and Z. As a developer, do you even know what they're talking about? So if someone came to me and they were going to do, I don't know, they're going to do software to manage a winery, right? The fermentation process and all this other stuff. They're going to use really specialized terms that people who make wine, what are they called? Vintners? People who make wine use. And I won't know any of those terms. And I'm going to use really specialized terms about my software, and they won't know those terms. Right? So the problem is we don't know anything about each other's work. How are you going to bridge that gap? That could be tough. That can be tough. Someone comes to you from a different knowledge domain, farming, business, fashion. What's the word? Customer relation management. It's a big deal now. I don't know anything about that stuff. So they have to tell me, okay, here's what I want, but somehow we have to know. Somehow we have to know. Let me explain what's happening with the dogs, by the way. My wife left and she went in the car and went away, and the dogs are convinced she's like just in the garage waiting for them, right? So they keep running back and forth, assuming that they're going to get to go out. So apologies for that. Anyway, how do you know that stuff? And then how do you know that you understand what they want? How do they know what can be done? They don't know what software can do necessarily. Some people have these really exaggerated, fanciful views of what software can do. And by the way, you have to be on guard for that. Whenever you're in a meeting and someone starts out a sentence by saying, well, all we have to do is get the software guys to, then you better listen, because they might ask you to do the impossible. And it's a good thing right in that meeting. No, we can't do that. No, nobody can do that. Okay, so that's the first problem. Now, here's different ways that people have resolved this. Sometimes, and again, I'm assuming the customer is actually the user here. It gets more complicated when the customer is the user, is not the user. So now the customer is actually buying the product and they're going to use the product. Maybe. But one thing you can do is and people don't do this very much, by the way, but they should, and it's getting to be more popular. You take a software developer, or you take a member of your team, and you send them to that company for a month. And all they do is walk around that company and ask people questions. Hey, how do you do your job? What does your software do? What do you like about your software? What do you hate about your software? What do you do? You know, what's your routine? What's the first thing you do in the morning? You know, turn on the coffee pot, whatever. Now you have an idea. Right? So the idea is to build this relationship between the customer and the developer. And Agile has a lot of things embedded in it that does that. Now, what if the customer is not the actual end user? For example, I've already complained about the software Embry-Riddle was. Embry-Riddle just bought this software called Workday, and I'm one of the end users of Workday. I didn't get a voice in the selection, right? I think they talked to some faculty, but maybe not. So the idea here is the customer was Embry-Riddle, but the user are faculty members and admins who have to use Workday. And I don't know anything about Workday right now, you know, because I have to take some training classes. I might hate it. I might love it. So the customer maybe didn't know what the end user really needed. This is, by the way, a really common problem, really common problem. So the idea is the customer may have an issue with understanding what software can do and how to explain it in software terms. The software people will have no understanding of what the customer's business domain is and how to use terminology that makes sense to them. And then the end user may be a whole different person who didn't even get a choice in this and said, this is just, you know, this isn't what I needed at all. It's not hard to find examples of that. You all use Canvas, right? You're a user of Canvas. Who is the customer? Embry-Riddle. Embry-Riddle bought Canvas, and then they gave it to you and said, thou shalt use. Now, there are things about Canvas that I like a lot. I think it's a pretty good system, but things about Canvas I don't like a lot. So how does Canvas, the people who develop Canvas, how do you think they resolve that, where there's weaknesses in their software? What do you think?
Is there like a feedback system?
Yeah, there's
user
a
feedback.
yeah.
There we go.
They're just sitting there counting their money, right? They don't care. No, there's a feedback system. So there's a Canvas community, and people can say, hey, I'm a professor at so-and-so, and it would be really cool if I could do this, or it would be really cool if I could do that. And then they can take that into account for their next release. And there's also locally a feedback system. So IT can manage stuff that happens in Canvas to some degree. And we can go to our IT and say, in fact, this happened just recently, not with Canvas, but with another system, where we said, hey, this isn't the way we need it to be. And IT said, okay, we can fix that. And they actually, you know, they fixed it within about a day. Tough stuff. Again, stuff you tend not to think of in academia, because who is your customer and user when you were developing, say, a homework assignment where you had to do a program for a homework assignment? Customer was your grader, I would say, right? But you're kind of the user and the developer all in one, in the sense that nobody really used the thing. You were kind of your own customer almost. You're just hoping to pass it off to the grader and get it graded. But there wasn't a whole lot of interaction because we don't get an opportunity in academia very often to do things that are sophisticated enough to bring these problems out. And hopefully that's what this class can do, is get you to do something sophisticated enough to bring these problems out. Not to where they, you know, kill your grade or anything, but where you experience what these things are and then overcome them. Okay, teams. I want to talk about teams for a little bit. This is an important thing. I don't know, maybe I should have highlighted it or something. What is a team? You all know what a team is. Now let's explicitly know what a team is. Clearly more than one person, even though what's the slogan? Army of one? Even though Army of one, right? More than one person working on a single goal or task with assigned roles dependent on one another. If any one of those things are missing, you don't have a team. So a bunch of people studying in the library on their own, for their own tests, they're not a team. because they're not sharing the goal. They're all working on their own individual homework or their own individual test. Assigned roles, if you don't have assigned roles. Now this is a loose term. I don't mean that, the leader of the team is a dictator. You do this and you do this and you do this. But the team will assign roles. Now in Agile, you do a lot of self-assignment, right? You volunteer for things and so you become assigned that way, but you do have a distinct recognized role in the team. And then you have to be dependent on each other. Again, if you're not dependent on each other, it's not a team. It's just a bunch of people doing stuff. So, faculty of the EECS department, are we a team? Sure, there's more than one of us. We have a single goal, which is to give you a good education in our respective curricula. Assigned roles, we're all assigned classes, and then we have other duties beyond that. And we are dependent on each other. If I do a lousy job in this class of delivering this class and getting these concepts through to you, you better know that I'm going to hear about it from Omar Ochoa when you go into his class next. And if you know Dr. Ochoa, you know I'm not kidding, right? He'll come and tell me about it. My chair will also tell me about it. Okay. So the reason I want to talk about teams, and we'll talk a little bit more as we talk about the project, is you get to work on a team in this class, and we don't want to have that lousy academic experience where you've got a team of 5 people and 2 people did all the work and 5 people get credit. That's no good. That is not acceptable for anybody. Okay? The goal here is to get 4 people working on a team where you really do have the experience of working on a good team. How many of you guys have worked on a lousy team in your past experience in academia? Yeah, it's pretty normal. That's a normal academic experience. How many of you guys have worked on a really good team, either in academia or in, maybe you were in a club, you're in Boy Scouts, Cub Scouts, or you're on a basketball team or something like that. A good team, right? And man, being on a good team, oh, many times. Okay. That's good. So whoever gets John on their team, John Mueller says many times. So John might be the thing that made it all work. Right? So yeah, it's easier to have a bad team than a good team. So we want you to be aware of team dynamics, how things work, give you tools. If things are not going well, if someone's not pulling their weight, how can we address that? How can we get them back into the fold? That kind of thing. We have to have a little flexibility because, if one of your team members has to take care of a sick family member or something like that, we have to have a little flexibility. But at the same time, what we want to do is build up a good interaction between your team. And fortunately, the Agile process is pretty well suited to that. What issues do we have with the teams? Formation and building, technical competencies. That can be the big one. A young software company, they want to get their first big contract. So no matter what the customer says, no. Chris Stockwell, if you're looking in chat, corporal punishment works pretty well. No. If they want to get that big contract, and so someone says, hey, can you do this for us? And they're like, sure, we can. And then, we have no idea how to do this. You want to make sure that you don't overpromise what you're going to do and make sure you have the technical competencies. And again, if you're dealing with something new to try to stretch your business, that might mean you hire on some new experts for short term. You get some consultants or something like that. Shared situational awareness is another one. Is the team really driving at one goal? We think that's the goal. Heck, just today I was in a meeting and someone said, well, Dr. Garfield's going to give this presentation during this meeting. And I was like, no one told Dr. Garfield that that I was going to give a presentation in this meeting. So I said, I was not aware of that and I'm not going to do it. That's shared situational awareness breaking down right there in that team. So the idea is, you're constantly kind of checking with each other. Here's where we are. Here's what we think we're going to do next, that kind of thing. And you do this through communication. Now, the way Agile works, ideally, it's all about communication. And ideally, in a pure Agile process, you're working physically in the same room. Teams share the same room. And you'd be amazed if you're writing your software or you're doing your design in the same room, how much that helps. Because right there, you've got, say, 5 people on the team and you're thinking, well, man, I got trouble with this, so-and-so, could you help me? You step over to the whiteboard, ... Oh, that makes sense. Take a picture. That's your documentation. Go back and do it. The next day I'm out sick, but this work still needs to be done. Guess what? The person who helped me yesterday can carry on with the work. It's called osmotic communication. Just by the fact that you're being together and you're asking each other questions really quickly, you're sharing a lot of information. And it helps the team have shared situational awareness. It also helps the team be more robust. If somebody has to leave the team for whatever reason, the other people have an understanding of what that person was doing. Believe me, there's a lot of times where you get on these, someone who leaves the team and then everyone else is like, I have no idea what that person was doing. And then you have to try to figure out what they were doing and make it work with the rest of the team. No, all of these in chat, approvals of corporal punishment. No, that's not going to work for this class. No. We have more productive ways to help people become productive. All right, software quality. This is all part of software engineering discipline again. Different views. How well does the software satisfy the customer or the user? Remember, the customer and the user are not necessarily the same thing. How effective was the development? Now, that's a weird question. Right? If you can get that one wrong. How effective was the development? If the development was smooth as silk, everything went fine, we're on time, under budget, but the customer is furious at us, was it really effective development? So there's an aspect of how the process went there, but there's also an aspect of customer satisfaction there. And then how easy it to use and maintain, which again, in academia, we don't get to deal with too often. So we have quality of product, process, and quality related to the business environment. How much money are we going to make off this thing? Some characteristics that people deal with: reliability. You know this. You may have changed cell phone providers because one of them was not providing you reliable service. I go around town, I can't make any phone calls, so I change. Or you may have cable companies with outages. They're not so common as they used to be. Efficiency does not waste computer resources, space, and time. This one, we used to worry about that all the time back when computers were slow and didn't have any memory. Now that chips are fast and memory is cheap, that one has become a little bit less of a driver. Now, there still are applications where it's a driver. So you have these massive systems now where they're vacuuming up all this data from the internet and doing horrible social engineering experiments on us. These are massive systems. The NSA is doing massive data sweeps around the world. These are large systems. And here you still want efficiency. Again, maintainability and usability. Notice how these things keep coming up. Additional ones. Now, these are the ones we're going to be interested in, I think. Easy to understand, easy to test, low cost. Well, other than your time, it's free. Reusable. Now, that one, I don't know, for your projects may not be something that we can deal with too much. But if you pick your project in such a way that you want to extend it or you want to adapt it to another situation, I'm going to do the project here, but now I've got another project that I want to do for my own later on. Maybe you want to deal with, worry about how much is reusable. Remember, one of the promises of the object-oriented paradigm was everything was going to be reusable, and that's not true. We get most of our reuse through inheritance. Delivered on time and portable. So one good thing about the agile process, this delivery on time works. So what you do in a normal project or in a pre-agile world is you would say the software has to do these 90 things and we're going to deliver it in a year. And at the end of the year, you're not done. So you go another year. And finally, after 2 years, you delivered 90 things. What Agile says is this: we want to deliver these 90 things and we're going to be done in a year. At the end of the year, if we only have 85 things done, oh well, we're done. It's a nice system in that it manages your schedule well because it time boxes it. So here, we've got till May 3rd or something like that. At the May 3rd, we're done. And if you manage your process right, there will be things that you promised at the beginning of the semester that you didn't deliver. And I'll say, that's fine because you managed the process and you told me ahead of time this wasn't going to happen. Now there's a dividing line there, right? You said, okay, it's going to do these 50 things and it does one of them. No, that's not good software quality. But you said we wanted to do 50 things. Let's break it down into 40 things we know we can do and 10 things we'd like it to do. And you deliver those 40 things, or maybe 42. You've done what you said you were going to do. You deliver, you manage these things. All right. Summary. I'm not going to go over the summary because it's a summary. That's a lot of talking. Do we have questions? These things are good to think through as you're going through your project, and I will have assignments to encourage you to think along these lines. Can you identify where you're having these issues? Can you identify where you're having these issues? Other questions about this topic? Other questions about any topic in the class?
I have one specific to me, if you can stick around afterwards for a little bit.
Yep. Okay. All right. We've gone an hour and 11 minutes. That's probably how long we'll go every day. And after that, everyone's brain is mush anyway. So without having some kind of, it's hard to get a, normally we would break this up in a classroom setting with some kind of a in-class activity. I haven't figured out how to do that online yet with you guys, but we can maybe experiment along the way. All right, thanks for being here. I'm going to stop sharing my screen. I'm not going to end the meeting though, but I will stop recording.